Welcome to our video on photonic filters. Today we'll be describing their operation, behavior, and the mathematics used to model them.
Hello, and welcome to the discovery of photonic filters. You may be wondering what this unknown material is, and through this video we will explore the fundamentals to this topic. To start off, the basis to these filters are centered around these photonic crystals. These crystals were first introduced by Elie Abanovich and Sajiv John in 1987. These crystals are made up of nanoscale structures which will either allow or block individual wavelengths of light, based on their frequency of their dielectric constants. Waveforms that can pass through these structures are called modes. These waveforms are compatible with the dielectric fields of the crystal. A group of these modes are called bands. The wavelengths that cannot pass through the structure are known as photonic band gaps, which is exactly what we will be looking at through this discovery. Here is a picture of the first photonic filter. This 3D structure was made up of plastic with a forbidden frequency band in the microwave range. Most importantly, why are photonic crystals useful? These crystals, which are periodic or metallic in structure, are artificially designed to control the propagation of waves, thus allow researchers to manipulate the passage of electromagnetic radiation. What makes them interesting? Well, photonic crystals contain two or more different materials. Their behavior when propagating through light shows formal similarity to that of electrons in a semiconductor, which results in the formation of pass bands and forbidden bands over a range of frequencies. Therefore, the crystals have many interesting characteristics, such as an abnormal Lamb effect and superrefraction effect. In addition to the discovery of photonic filters, at the same time research went into another medium called the left-handed material, which basically demonstrates a material that has electromagnetic properties that are distinct from any known material, as can be seen from the photo. Next, we will explore the possibility of introducing point and line defects, which could possibly create pass bands within the photonic band gap. A photonic crystal with this band gap is expected to be a new material that can control the propagation of light, and since these photonic band gaps can prohibit any propagation of light in the forbidden bands, while allowing other wavelengths to penetrate through freely. Thus, these can be used as a band pass filter.
Photonic filters are mainly used in the industry as microwave or radio frequency filters. This is due to their low loss, high bandwidth, and immunity for electromagnetic waves. These filters allow signals with frequencies ranging in the mega to gigahertz to pass through. Applications of photonic filters include ground radars, which identify targets of interest by transmitting signals and examining their response to determine the spectral signature of each object. Moving on. Broadband wireless networks, spanning from wireless local area networks to universal mobile communication systems, and noise suppression for antennas that are used for receiving signals. Photonic filters are also made in the form of integrated circuits, where they're used to amplify frequencies and provide chip coupling and routing from one electric component to another.
Now we will get into some of the math we will be using in order to analyze this structure. Here is a diagram of the structure showing all three layers we'll be stimulating with the material. We have layers A and B with refraction indices N1 and N2 and thicknesses D1 and D2. A and B need to have the relationships such that D1N1 is equal to D2N2. C, of note, is a left-hand material which gives it different properties of A and B as explained earlier in the video. The N3 of C is meant to be greater than 0 always, and in order to analyze this whole system we will need to use the transfer matrix method. Here's the formula we will be using the transverse matrix method for in order to analyze the band gap characteristics. It consists of AB of K is equal to AB of M times C times BA of N, where M and N are the cycles. The matrix A consists of cos delta A, negative I over eta A, sine delta A, negative I N or eta A, sine delta A, and cos delta A. It is important to note that the incident wave is in transverse electrical mode, which gives us the formulas here of eta A equal to the square root of epsilon over mu cos theta, and delta A equal to 2 pi over lambda n1 d1 cos theta. The matrix and formulas are the same for B as they are for A, but with delta B, A to B, N2, and D2 instead of the A equivalents. Matrix C, on the other hand, however, represents the material C, which happens to be a left-handed material, and therefore must be taken into separate consideration from A and B. In order to do this, we use the transfer matrix, represented here, from a normal medium to a left-handed medium, which consists entirely of ratios of reflectance and transmission rate. The reflectance is the measure of the amount of light or other radiation reflected off a surface, whereas the transmission rate is the speed at which light and other radiation can be transmitted. After determining matrix A, B, and C, we now have the final transfer matrix M, which determines the properties of the photonic band gap. Two of these properties would be the total reflectance and the total transmission rate of the entire system, where M11, M12, M21, and M22 are the indices of the matrix M. After we have determined matrices MA, MB, and MC, we now have the final transfer matrix M, which determines the properties of the photonic band gap. Two of these properties would be the total reflectance and total transmission rate of the entire system, where M11, M12, M21, and M22 are indices of the matrix M.
To conclude, after the discovery of photonic filters, their microstructure led to fascinating applications, as well as the discovery of left-handed materials. In the video, we explored the use in real-world applications, the link between their behavior and the material characteristics, as well as the mathematical properties of photonic filters that make them very useful to us. We hope you enjoyed our presentation. Thank you for listening.